So the question is, when you are designing a loudspeaker, perhaps you already have some of the design, how do you make it as best as possible? How do you even know what kind of response it gets? And one way that we'll just look at later is using simulations instead of building the entire speaker and then measuring. And that could be loudspeakers as for the home. It could be loudspeakers in cars. It could be any type of loudspeaker that we're interested in, for headphones, earphones, whatever. The idea is to first have a CAD file that has the geometry of the loudspeaker. So you'll typically have like a cone, a dust cap, a surround all the way around here, and a spider adding some stiffness and control to the overall system, and a what's called a former and a voice coil. So you put some voltage on the voice coil. The voice coil sits in a magnet system that we can see outlined here. And as the current in the coil changes with the music, the voice coil is being moved in and out, and so is the cone, and that is what generates the sound. So we can build a virtual loudspeaker in a simulation software like COMSOL Multiphysics, like I have here. In this case, it's a very simple 2D axis symmetry case that they have made themselves, and that's what I'm showing here. We see the magnet system again. We have our voice coil, our former sitting here, our very simple spider, and here we have the cone and the surround, and it's sitting in a baffle. So we are measuring or simulating corresponding to a measurement where we have a baffle. And the larger domain here is air. So we are making sound that propagates out in the air, and it has to stop somewhere in the simulation. So we have ways of having the sound field just propagate outwards from here. And when we do the simulation, there's a lot of setup. So we have some materials over here, air, we have some material parameters for the magnet system, for the cone and the surround and other parts. So you can see there are a lot of material input that you have to know for a loudspeaker. And then you set up the physics. In this case, we have magnetics included. Of course, there's a lot of setup with that. You have to say this is a magnet, this is a coil, and what kind of windings you have, how many. We have the pressure acoustics. That's where I said the larger domain here is air. For that, we have a density and a sound speed. We also have some other calculation boundaries that we use later on. And we have the solid mechanics, so that's the moving structure, in this case the cone and so on, which is moving in and out, generating the sound pressure. For these types of simulations, we always have this mesh that we have to make, and there are certain rules of thumb as to how refined the mesh needs to be, and that depends on how high you go up in frequency. And then you are pretty much set to go. You need to make some kind of study now, and we typically make a frequency domain study because we're interested in frequency response. What type of sound pressure level do we get across a frequency range of maybe the entire audio frequencies? We do the calculation. There's no need to do it now, but this one is very simple and only takes a minute. That means if there's something you want to change later on, like a new cone material, it only takes 1 more minute to figure out what is this new response. So with simulations, you can make many iterations fast, and you can sweep across many different situations, many different materials. Not necessarily in 1 minute, because this is a very simple case, but pretty much always faster than you could manufacture a prototype physically. So once you have calculated or run the simulation, you can see things like magnet field and the different effects associated with that. You have a high concentration of the magnet field here in the gap, as you want to, because that's where the coil is. You can see many other things related to the magnetics, like skin effects and things. And then you can post-process, for example, the coil inductance and resistance, whatever parameters that are related to the coil. And so you could change the number of windings in the coil and rerun the simulation and get a new curve. The typical area of interest is, of course, the sound pressure level, because that's what we hear. And we can look at it at different frequencies that we decide ourselves. And then we can animate. If I make an animation here, take the player and take the window we had before. Sound pressure should actually be sound pressure level for us to see anything. So let's change to sound pressure level. Sound pressure. It should be sound pressure, not level. And then we can animate. So we run the animation. Takes a little time every time. And hopefully we see that we have waves going outwards. We can change, if it's difficult to see what's going on, we can manually change the range here. So we could say -5 and 5. And then animate once more and see what happens here. So a lot of times you're visualizing things in a way that makes it easier for you to see what's going on. You exaggerate different things. And here you can see that the sound pressure is moving outwards away from the cone. And that is also what we have and what we want to see. And then you can say, okay, what is the sound pressure level? And you can even find it outside of this sphere here. So you can go 1 meter away, which is certainly not inside the sphere. And that's what we have here, sensitivity. And I don't even know what they have chosen, but you can visualize it in different ways. So you can see that it rolls off below 100 Hertz. It has some variations here at higher frequencies. You probably have some modal behavior going on. And you can run again with different geometries or different materials, and then see if your response is any better. And there are different ways to analyze in more detail what is going on at these frequencies. Probably have an electrical impedance too, where you can see at a certain frequency you have a peak in the impedance. That's where it's very easy to move the driver at this frequency because of the mechanical setup. And then you could potentially put that loudspeaker into a car somewhere, and then do more calculations to see what kind of sound pressure do you now get inside of this car. So you can do simulations in step that way. And finally, and of course you could you could also now go in and see what is the sound pressure level at the front seats or the rear seats or wherever you want to. And then you could potentially look into waveguide design and other types of design, perhaps via optimization. So you have a driver down here, and then you have some geometry here leading out to the outside world, and you want to generate a flat sound pressure level somewhere, and then you can set these boundaries free and manipulate them and warp them, and end up with different shapes that we can see here, that the simulation has been set up in a way so that it's allowed to change the original geometry. So you can see it has a different shape, and we're looking at 1/2, that's why it's cut here. So we have symmetry, and you can have different targets. In this case they have made 2 different variations, one where they go for a good on-axis pressure, and another one where it's off-axis pressure, and you can see that they get a different shape. So there are many options and many ways to manipulate things in a simulation that would take you very long to build in a physical setup. And that's the main idea with doing simulations. That is that you make a geometry, you make sure that it's easy to mesh, as we saw before, and you try out different things in a virtual world instead of a physical world. And then of course in the end you build the prototype and you see if you have a good match with the simulation, and typically you do. So you can get very far with simulations, maybe starting from scratch, or maybe starting from a physical prototype that you have. So that is basically it.